Alright, welcome to the second lecture on Jordan algebras. Today what I'd like to do is go over a theorem of Jacobson and Rickart, which gives some feeling as to how much of the structure in an associative algebra is captured by the Jordan product. To begin, let me just make a quick review. So recall that if A, let's say it like this, recall that we define a special Jordan algebra is a linear subspace of an associative F algebra A such that it is closed under these two particular compositions. So under the operation, so there's the unary operation of taking an element to its square, and the binary operation of taking a pair of elements AB to this product ABA. So a special Jordan algebra, by definition, is a subspace of an associative algebra which is closed under these two operations. And we say that that F from J to R, a linear map of special Jordan algebras, is a homomorphism if, actually let me call it sigma like I was doing before. It's a homomorphism if it preserves these two operations. So that is to say, if you taking the square of an element and applying sigma to it is the same as applying sigma first and then squaring, and if doing ABA sigma is the same as sigma applied to A, sigma applied to B, sigma applied to A. Okay, so that's the notion of a special Jordan algebra. In particular, any associative algebra is a special Jordan algebra, just because it's closed under all these things, right? And one can also talk about Jordan homomorphisms, or probably I should say special Jordan homomorphisms, between associative algebras. And the theorem of Jacobson and Rickart describes really, or shows you what the constraints are on homomorphisms, which are Jordan homomorphisms, between associative algebras. So here's the theorem. Jacobson and Rickart. So let A and B be associative algebras, and suppose B has no zerodivisors. Otherwise, the statement is just a lot more complicated. And suppose that sigma from A to B is a special Jordan homomorphism. In other words, it's a homomorphism which preserves not the structure of the associative algebra, but simply the structure of the special Jordan algebras. It preserves these operations of squaring and the triple product thing ABA. Okay, then either sigma is an associative algebra homomorphism, that in fact either it preserves the structure of the associative algebra or it's an anti-homomorphism. So recall that an anti-homomorphism is the same as a homomorphism except instead of preserving the multiplication, it reverses the order of the multiplication. So it's a homomorphism from the algebra to its opposite, if you will. So in other words, anti-homomorphism means that if I apply it to AB, then instead of getting A sigma B sigma, I get B sigma A sigma. Okay. So that's an anti-homomorphism. Okay. So, but what this is saying is that, in fact, the Jordan structure, the structure that's preserved by these Jordan, or that is encoded in these new operations of squaring and taking AB to ABA, well, it's not everything. I mean, you can't recover the original algebra structure, otherwise a Jordan homomorphism would have to be an actual homomorphism, but it's very close. The only thing that you're forgetting is the difference between AB and BA. Other than that, it's a homomorphism. Other than that, you've encoded the structure. Okay, so let's prove this, and I have to erase everything to give myself some room. So we want to suppose that we have some sigma from A to B, which is a special Jordan homomorphism. And the first thing that I'll do is let me just give some identities that'll make things a little bit easier to think. So notice that the operation AB plus BA, the kind of symmetrized multiplication, but without dividing by 2 now, just the AB plus BA, I can always write in terms of the Jordan operations that I have. This is always A plus B squared minus A squared minus B squared. Right? It's just, if I remove everything but the cross terms, then I get AB plus BA. I can always get that. Or describe this operation in terms of the Jordan structure. And in terms of the ABA, well, notice that if you look at, let's say, A plus CB times A plus C, so if you do the, let me just kind of like leave this on the side. So this is like the new operation over here that we've written in terms of the old one. Then this is kind of going to be the old part that we're going to write, we're going to get some new thing out of. So if I look at A plus CB, A plus C, what is that? Just work it out. This is AB plus CB times A plus C, which is ABA plus CBA plus ABC plus CBC. And what I'd like to point out is that two of these things are just kind of Jordan structure things, and 2 of them aren't. So this aren't visibly such. So these 2 things are easily described in terms of the Jordan product. And so what I see is that if I look at A plus CB, A plus C, this is something, in terms of the Jordan structure, and I subtract off ABA and I subtract off CBC, then what I obtain is this new combination, ABC plus CBA. So that is to say that this new thing, ABC plus CBA, can be written in terms of these old Jordan things. So this can be written in terms of that. This that can be written in terms of that. Okay. So really, I can record this by saying that I have these new structures, AB plus BA, this binary composition, and this thing, ABC plus CBA, this trinary composition? Yeah, let's just say trinary composition, which have the property that if I preserve my Jordan structure, I necessarily preserve this binary thing and this trinary thing also, because they can be written in terms of the Jordan structure. Okay. So the point of all that work was just to write that these 2 things are also preserved. And what next? Well, Now, what I'm going to use, let me just to be very clear, what did I really say? I'm really saying that if I look at AB plus BA and I apply sigma to it, then because this can be rewritten in terms of things involving the Jordan structure, then that's the same as AB plus B sigma, A sigma B sigma plus B sigma A sigma. And similarly, this thing has that property, that because I can rewrite it in terms of the Jordan structure, that if I apply sigma to that, I necessarily will get A sigma B sigma C sigma plus C sigma B sigma A sigma. Okay, that's really the conclusion. Okay, now what am I going to do next? Well, we want to prove that sigma is either a homomorphism or an anti-homomorphism. So the way to do it is we construct what I'd like to call a homomorphism, anti-homomorphism detector element. Okay, so we have, given our elements A and B, let's say we want to tell if it's a homomorphism or an anti-homomorphism. Well, what you do is you look at sigma applied to AB, subtract sigma applied to A and sigma applied to B. We would like to show that that's 0. Well, if that was 0, that would mean that sigma acts like a homomorphism on AB. Maybe it will and maybe it won't. I mean, because maybe this is 0, or maybe actually this is 0. Because maybe it's an anti-homomorphism, not a homomorphism. One of these two things should be 0. Well, let's just say that the product should be 0, therefore, right? And because we're mapping into a domain B, remember B is a domain, it doesn't have any zerodivisors, then really what we're saying is that if we can show this thing is 0, we'll have shown that either one or the other is 0. And while that's not the same as showing that it's always this or always that 0, it's at least the first step, okay? So this is our starting point. We're going to show that this is 0. How do we do it? Well, just do it. Let's do it. So what is this? This is AB sigma times AB sigma, so it's AB sigma squared. It's AB sigma, so AB sigma, and then B sigma A sigma, and it's these two, it's minus A sigma B sigma times AB sigma plus A sigma B sigma squared A sigma. Okay, now, by the, because sigma is a Jordan homomorphism, it preserves squaring, so I can move this thing inside, and I have AB squared sigma. Okay, and now what I want to do is I want to look at this animal here, and I'm going to use this identity. So I'm going to use this identity where, let's say, well, let me pull out a minus sign to make it look a little bit prettier. So this is all minus, what do we have? I'll put this one first and this one second. We have an A sigma, B sigma, AB sigma, and now plus this guy here, which is an AB sigma, B sigma, A sigma. Let me finish off by writing what that term is over there. This is A sigma, B sigma squared, A sigma. Okay, now check it out. We've got here the same B sigma in the middle everywhere. Here I have an A sigma on the left, here I have it on the right, and the AB sigma is on the one hand on the left and on the right. This is this identity where this is my A, this is my B, and this is my C. Well, what I know is that if I have sigmas over those, I can pull them all out. So let me do that. So let's say AB squared sigma minus, and I'm going to pull my sigmas out of this whole thing. Give myself AB plus AB BA, sigma on everything. Now this thing over here, I can move the sigma past the squaring because sigma preserves squaring, so I can rewrite that like this. And now what I have, wait, should I have done that? Oh, I should have, but I didn't do anything. I just copied the same thing twice. I'm going to move the squaring on the inside. Okay, now what I have is I have the the ABA thing, but with the B squared instead. Doing sigma preserves that, so I can pull the sigma out. So that gives me an A B squared A to the sigma. Okay. Now, I can take this thing and I can move the sigma out of everything, right? Because sigma is linear and I'm just looking at a sum and difference of some stuff. So let me pull a sigma out throughout this whole thing. And now, we have 0. Because what is this? This is, maybe it's a little bit too low to read very well. So, so this whole thing is equal to that. And maybe I'll finish this off over here. This is, what is it? It's sigma on the outside, but on the inside is this, what is it, AB squared. This is a minus AB squared. I get a plus ABBA. Oh, but it's really a minus that. Minus AB squared A. Inside we're in associative algebra, right? And now plus AB squared A. Sigma on everything is 0. So this thing is equal to 0. So what does that tell me? The conclusion is that for all A and B and A, either, because B is a domain, either AB, this sigma is A sigma B sigma, or it's B sigma A sigma. That's just on an element by element basis. We need to show that this happens uniformly for either one way or the other for all pairs of elements in A. Okay, so we'll do that next.